Question 3, Part A. Describe what is meant by dynamic equilibrium. Dynamic equilibriums, there are two items there, dynamics and equilibrium. So what is dynamics? Dynamic is always moving or is always forming. So what is the things that forming? Is the reactants and the products. Equilibrium is more towards the concentration. And if you want to give the complete definition or the meanings of this dynamic equilibrium, you must relate to these two items, rates and the concentration. So the full definition is the rates of forwards and reverse reactions equal, and the concentration of reactants and products remain constant. So there are two different things, equal and constant. So equal means, if let's say we have an equilibrium A form B. So we have forward reaction and backwards reaction. The rates for the forward and reverse reaction means the numbers of moles that form over time for these reactants and the products, forward and backwards, they are the same. So this we call the rates equal. Concentration, it not necessarily must be equal. Means it can be different concentration as long the concentration stay constant. For example, if let's say now for this equilibrium A, the concentration, it can be 0.5, B, it can be 0.25. As long the concentration of A, which is 0.5 mole per dm cube, B, which is 0.25 mole per dm cube, that stay constant, means same value. So we say that it's already reached equilibrium. That's the meaning. It's not necessary to be 0.5 or 0.25. This is just example. So means the concentration no need to be equal, but the rates for the forwards and reverse must be equal. That's the difference. I will understand what I say. Part B, reaction 4. This one. Describe the reversible reaction between the yellow iron 3 and the colorless SCN negative, which produce these products. Okay. The Fe SCN2 positive, so which is red color. So we have two color compound. Okay, so it's iron 3 yellow and the product which is red. Now, an equilibrium contains iron 3 and the SCN negative and the Fe SCN2 positive. A few colorless crystal of soluble KSCN solid are added. The mixture is left until it reaches equilibrium again. The temperatures for the both equilibrium mixture is the same. This is very important. This one is telling you the Kc no change. Kc is constant. Now, the one that added is actually the SCN negative, because when this salt dissociate, it will produce this anion. When this anion increases, the equilibrium will shift to right hand side to reduce the concentration of this anion. So therefore, we know that now the color change, it should be darker red. Once it's reached a new equilibrium, because the equilibrium shift to right hand side, which is more towards red color, so the color change must be darker red. Right, so the part 1 here, deduce the change that occur, if any, in the equilibrium mixture after the solids added. So change in appearance must be darker red, because more of these products form, which is red color. Second part, change in the relative concentration of iron 3. Of course, when the equilibrium shift to right, the concentration of iron 3 will decrease. Okay, so very easy, this one. The change in the value of Kc. As long the temperature same, the Kc stay constant, right? So no change. Okay, so you guys just need to remember this. Whenever temperature no change, same temperature, Kc must be constant. Okay, part 2. Now we have the expression, Kc expression for the reaction for just now. Okay, you just follow this one, used for the calculations later. So now, let's start with the first statement, the concentration or the moles that involved. Is given 5 times 10 power negative 5 mole of iron 3 and 5 times 10 power negative 5 moles of the anion, right, the SCN negative, added together and allowed to reach equilibrium. Means it's telling you initially it just involved the iron 3 and the anion, and the product still not yet formed, 0 concentration. And this one is a very important information, is telling you the concentration. So the total volume of the mixture is 25 cm cube. So you can now calculate the concentration for the reactants, means for these two reactants. Okay, later I'll tell you how to do this one, the ICE table. At equilibriums, the concentration of the product is 4.23 times 10 power negative 4 mole per dm cube. Calculate the Kc for this reaction. Okay, so let's focus on the ICE table. Okay, first, if you want to calculate or you want to get the Kc nicely, it's better for you to construct the ICE table. Then you can get the answers faster, right? Now, let's start with this equilibrium. Okay, still the same reactants and products. Okay, I means initial. So initial concentration. So we use the moles that given over the volume in dm cube, because it's mole per dm cube, isn't it? So therefore, for both reactants, you will get 2 times 10 power negative 3 mole per dm cube. Concentration for the product, 0. So later we will discuss about the change. C means change. E is at equilibrium. At equilibrium, already told you just now, the product's concentration is this one. So you just put the values here. 4.23 times 10 power negative 4. So this is the one that you must put initially. Initial and the equilibrium. So the change now is very obvious. Since the product's concentration is 4.23 times 10 power negative 4, therefore the change must be plus 4.23 times 10 power negative 4 mole per dm cube. If this one, the value is 4.23 times 10 power negative 4, the reactants also need to minus the same amount or same concentration. So means you need to use 2 times 10 power negative 3, the initial concentration, minus the concentration now. So therefore, you get 1.577 times 10 power negative 3 for both reactants. So once you obtain these two concentration, then you can substitute to the Kc expression. So 4.2 3 times 10 to the 4 over 1.577 times 10 to the negative 3 squared. So you get 170.1 per mole dm cube. This is a units that you must figure out. You just need to use this mole per dm cube over mole per dm cube bracket squared. So you get this one per mole dm cube. So unit is always 1 mark here, right? So if you're able to get this all this concentration and this concentration, and substitute to the Kc and get the correct units, you can get 4 marks. Okay, this is how to calculate the Kc for this reaction. Part C determines the full electronic configuration for iron 3. In order to figure out the full electronic configuration of this iron 3, of course it's better for you to know the iron. What is the electronic configuration for this iron? So it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 for s2. If this iron now ionize and form iron 3, so means 3 electrons removed. Electrons will remove from the 4s orbital or the subshell first, so means this one gone. Continue by 1 electrons from the 3d, so it becomes 3d5, right? So therefore for the iron 3 positive, so the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Part D. SCN negative is colorless, completes the dot cost diagram for this in this figure 3.1. So first you need to figure out the total electrons that you need to put into the diagram. Sulfur contribute 6, carbon contribute 4, nitrogen contribute 5. All this one you can get from the valence electrons. Okay, do not forget to plus 1 here because it's negative charge. So total electrons that you need to put into this figure 3.1 is 16. And of course, it's quite challenging to complete this diagram. Because you need to figure out whether there is a double bond, single bond or triple bond in the structure. It's better for you to start with the cyanide, because cyanide is a CN triple bond and is charged negative, and the carbon is the one that gains the, let's say now there is 1 electrons on the carbon, and carbons will gain 1 electrons from outside. So this is the cyanide ion. Imagine that this lone pair now is donates to the sulfur to form the dative bond. This is how the dot cost diagrams looks like. Of course, this dot cost diagram is not 100% correct. If you found out the diagram is something wrong, of course you can tell me, or you can suggest, no problem. For the carbon, it will share 3 electrons with the nitrogen, form the 3 bondings here, triple bond. And the nitrogens has 1 lone pair. So the nitrogens now is form octet. So total 8 electrons surrounding nitrogen. Carbon now it has 6 electrons here, and of course the 2 electrons that I told you just now. 1 electron from itself and 1 electron from outside. And these pair of electrons donates to the sulfur. Sulfur no need to share its electrons. So these 6 electrons, these 6 the unbonded electrons, so is from the sulfur, right? So it's a dative bond here. Okay, so this is the dot cost diagram. I hope you understand how to form this. Okay, that's all. Thank you.